Today we will discuss important important topics of green chemistry. Use of microwave energy in green processes. Use of microwaves in green processes. The main aim of the green chemistry to reduce or eliminate the use or generation of hazardous substances. So chemists must have to design, manufacture and develop some novel technology for preparing the chemical products. For fulfilling the desire, Einstein and Warner formulated 12 principles of green chemistry to shape the environment and can be considered as blueprint for practicing green chemistry. Out of these 12 principles, the following principles are taken care for microwave assisted synthesis: prevention of waste, less hazardous chemical synthesis, design for energy efficiency, inherent safer chemistry for accident prevention, reaction time is reduced, solvent-free reaction can be performed, and improved yield. What is the aim of this technique? In this technique, microwave radiation is used to carry out the chemical reaction. It has changed the way of conventional chemical synthesis dramatically. The conventional heating is inefficient and time consuming. With the help of saving time, now chemists can concentrate their creativity for developing their new invention. The problems related to waste disposal of solvents has been overcome by performing reactions without a solvent under microwave irradiation. The irradiation of microwave can be applied on the sample with mineral supported catalyst under solvent free condition, gives clean chemical processes with the advantage of enhanced reaction rates, higher yields, greater selectivity and greater ease of manipulation. Now, what is the microwave radiation? Microwave radiations are electromagnetic waves. Microwaves have wavelength of 1 millimeter to 1 meter, corresponding to frequencies between 300 megahertz to 300 gigahertz, and energy association 1.24 into 10 to the power minus 20, 10 to the power minus 3 to 1.24 into 10 to the power minus 6 electron volt. This is the region. In the electromagnetic spectrum, the microwave radiation region is located between infrared radiation and radio waves. Telecommunication and microwave radar equipments occupy many of the band frequencies in this region. Microwave dielectric heating uses the ability of some liquids and solids to transform electromagnetic radiation into heat to drive chemical reactions. This technology opens up new opportunities to to the synthetic chemist in the form of new reactions that are not possible using conventional heating. Microwave uses electromagnetic radiation that passes through the material and causes oscillation of molecules which produces heat. This is the spectrum, this is the region of microwave radiation from 300 megahertz to 300 gigahertz. Now the important point, the principle of this microwave energy use. The basic principle behind the heating in microwave oven is due to the interaction of charged particle of the reaction material with electromagnetic wavelength of particular frequency. The phenomena producing heat by electromagnetic radiation are either by collision or by conduction, sometimes by both. All the wave energy changes its polarity from positive to negative with each cycle of wave. This causes rapid orientation and reorientation of molecules which cause heating by collision. If the charged particles of materials are free to travel through the material, a current will induce which will travel in phase with the field. If charged particles are bound within the regions of materials, the electric field component will cause them to move until opposing force balancing the electric force. This is the irradiation and irradiate the molecules and ultimately gives the product. Now, the mechanism of microwave heating. In microwave if oven, material may be heated with use of high frequency electromagnetic waves. The heating arises from the interaction of electric field component of the wave with charged particle in the material. Two basic principal mechanism involved in the heating of the material. All materials are not susceptible to microwave heating as response of various materials to microwave radiation is diverse. Based on their response to microwaves, materials can be broadly classified as follows. The materials that reflect microwaves, for example, metals. Materials that absorb microwave, for example, solvent, and materials that transparent to microwaves, for example, Teflon, glass, and quartz. Microwave absorbing materials are utmost important for microwave chemistry, and three main different mechanisms are involved for their heating, namely dipolar polarization, conduction mechanism, and interfacial polarization. First of all, dipolar polarization. In this process, heat is generated in polar molecules when it is irradiated with microwaves. The molecule must be polar. The electric field component of the microwave radiation is responsible for heating rather than the magnetic field component. Due to exposure to an oscillating electromagnetic field of appropriate frequency, polar molecules will try to orient themselves parallel to the field. This regular orientation, instead of random orientation, stores potential energy in presence of applied field. If the direction of the applied field is changed slowly, the molecules will rotate properly to align along the direction of the field. If the direction of the field is changed quickly, the molecules will try to orient accordingly, but all the molecules may not be able to align with the field's direction. Such molecules may bump into the other molecules. In fact, potential energy of the molecules failing to align themselves along the field's direction does not match with the applied field. This excess potential energy is converted into the kinetic energy through collision among the molecules. This leads to microwave heating. Here, it may be noted that if the field oscillates too rapidly, the molecules cannot interact with the field and they remain randomly oriented. At such frequencies, no heating will occur. Now, the question, why the polar molecules unable to follow the field? Due to intermolecular forces, polar molecules experience inertia and are unable to follow the field. This results in random motion of particle, and this random interaction generates heat. Microwave radiation has the appropriate frequency 300 megahertz to 300 gigahertz to oscillate the polar particles and enable enough interparticle interaction. This makes it an ideal choice for heating polar solutions. In addition, the energy in microwave photons, that is 0.037 kilocalorie per mole, is very low relative to the typical energy required to break the molecular bond, which is 80 to 120 kilocalorie per mole. Therefore, microwave excitation of molecules does not affect the structure of organic molecule, and the interaction is purely kinetic. This makes it an ideal choice for heating polar solutions. Now, next, the conduction mechanism. In the conduction mechanism, generation of heat occurs through resistance to an electric current. Due to oscillating magnetic field, electrons or ions also oscillate in a conductor, which gives an electric current. This current faces internal resistance, which heats the conductor. During ionic conduction, completely dissolved charged particle, usually ions, oscillate back and forth under the influence of microwave radiation. This oscillation causes collisions of charged particles with neighboring molecules or atoms, which are ultimately responsible for creating heat energy. For example, if equal amount of distilled water and tap water are heated by microwave irradiation, more rapid heating will occur for the tap water because of its ionic content in addition to the dipolar rotation of water molecules. What happens during ionic conduction? Owing to translational motion of electric charge, under the application of electric field, ions cause increase of collision rate and convert kinetic energy to heat. We know, according to Arrhenius theory, this Arrhenius equation, from this equation it can be said for every 10 degree centigrade increase in temperature, the rate of reaction becomes twice. From here, we can see it easily. Interfacial polarization. This mechanism is important for system where a dielectric material is not homogeneous but consists of conducting inclusion of one dielectric in other. The interfacial polarization method can be considered as combination of both the conduction and dipolar polarization mechanism. It is important for heating system that comprise a conducting material dispersed in a non-conducting material. For example, consider the dispersion of metal particle in sulfur. Sulfur does not respond to microwaves, and metals reflect most of the microwaves energy they are exposed to. But combining the two makes them a good microwave absorbing materials. However, for this to take place, metals have to be used in powder form. This is because unlike a metal surface, metal powder is a good absorber of microwave radiation. It absorbs radiation and is heated by mechanism that is similar to dipolar polarization. The environment of metal powder acts as a solvent of polar molecules and restricts the motion of ions by forces that are equivalent to interparticle interaction in polar solvents. These restricting forces, under the effect of an oscillating field, induce a phase lag in the motion of ions, resulting in random motion of ions and ultimately heating of the system. Next, the important point, the effect of solvent. Every solvent have a different degree of polarity. Reagent molecules also have different dipole moments. During the microwave irradiation, every solvent and reagent will absorb microwave energy differently. Therefore, they will be affected either more or less by the changing microwave field. A solvent having more polarity will have a stronger dipole to cause more rotational movement in an effort to align with the changing field. A compound that is less polar, however, will not be as disturbed by changes of the field and therefore will not absorb as much microwave energy. Unfortunately, the polarity of the solvent is not only factor in determining the true absorbance of microwave energy, but it does provide a good frame of reference. Most organic solvents can be broken into three different categories: low, medium, or high absorber. The low absorbers are generally hydrocarbons, while the high absorbers are more polar compounds, such as most alcohols. Here is the table of absorbance level with solvents high, medium, and low. These are the absorbance level solvents. Tangent del value. In this connection, we would like to mention about the factors affecting 10 del value. As the term dielectric heating suggests, A material must possess certain dielectric properties in order to be efficiently heated in the microwave field. The heating characteristics of particular material, for example, a solvent under microwave irradiation conditions, are dependent on the ability of specific substances to convert electromagnetic energy into heat. This ability is determined by the so-called loss tangent. What is loss tangent? A measure of ability to absorb microwave energy and convert it into the thermal energy. We get derivation from Maxwell equation. Tan del is equal to loss factors divided by dielectric constant, and reaction medium with high tan del value will give efficient absorption and ultimately rapid heating. The solvent can be classified on the basis of tan del value. Classification of solvents with into high tan del value. Tan del greater than 0.5 is high, and medium where value is zero point 0.1 to 0.5, and low microwave absorbing where value is less than zero point 0.1. Solvents without dipole moment such as benzene and dioxane are more or less microwave transparent, which have tan del value less than 0.01. A solvent with high tan del value is required for rapid heating in microwave field. However, this does not mean that solvents with low tan del values cannot be used for microwave synthesis, since either substrates or reagents or catalysts are likely to be polar. The overall dielectric properties of the reaction mixture will in most cases allow sufficient heating by microwaves, even with non-polar solvents. If, however, the mixture is non-polar, passive heating elements can be added to aid heating process. Now, the important point: conventional and microwave heating comparison. Microwave heating is different from conventional heating in very respects. The mechanism behind microwave synthesis is quite different from conventional synthesis. We know that in conventional heating, container has to be heated first, then solvent heated. In this case, there occurs 90% loss of transfer energy. Only 10% heat will go to the solvent for solvent heating. So the process is not energy efficient. But microwave radiation process, container does not absorb heating. Heating occurs only inside. So it is energy efficient process. Here some points enlisted in the table as follows. Reaction mixture heating proceeds from the surface, usually inside surface of the reaction vessel, while for microwave, reaction mixture heating proceeds directly inside the mixture. For the conventional process, the vessel should be in physical contact with the surface source, that is at higher temperature source, for example metal, well bath, steam bath, etc. But for microwave heating, no need of physical contact of reactions with the higher temperature source, while vessel is kept in microwave cavities. And in conventional heating, by thermal and electric source heating takes place. But in the case of microwave heating, by electromagnetic wave heating takes place. For conventional process, heating mechanism involve conduction, but in the cases of But in the case of microwave radiation, heating mechanism involve dielectric polarization and conduction. Transfer of energy occurs from one. In the case of conventional heating, surface of the vessel to the mixture and eventually to reacting species. In the cases of microwave heating, the core mixture is heated directly while surface is source of loss of heat. In the conventional heating, the highest temperature for an open vessel that can be achieved is limited by boiling point of particular mixture. In microwaves, the temperature of mixture can be raised more than its boiling point. That is, superheating takes place. For the conventional process, heating rate is less, and for microwave, heating rate is several fold high. Here, some microwave assisted organic synthesis has been listed. Microwave assisted organic synthesis has been considered as one of the most research applications of microwaves in the chemical reactions. Chemists have successfully conducted a large range of organic reactions. There are some reaction takes place by the help of microwave radiations, just like dialkyl cellular reaction, Sek reaction, Suzuki reaction, Manich reaction, hydrogenation of beta lactams, hydrolysis, dehydration, esterification, cycloaddition reaction, epoxidation, reduction, condensation, protection and deprotection, cyclization reaction, and so many reactions can take place with the help of microwave radiation. Here I have given some example of microwave assisted organic synthesis, esterification reactions, hydrolysis reaction, oxidation reaction, decarboxylation reaction, cycloaddition reactions. This is the N-alkylation reaction, and Heck reactions can take place with the help of microwave irradiations. Suzuki reactions, here there are so many reaction takes place with the help of microwave radiation. Multi-component reactions, and there are some reactions that can occur in the absence of solvents also. Now, what is the benefits of microwave assisted synthesis? Microwaves can accelerate the rate of reaction, provide better yields and higher purity, uniform and selective heating with lower energy uses, achieve greater reproducibility of reactions, and help in developing convenient and clear synthetic routes. The main advantage of microwave assisted organic synthesis are given here. First of all, we'll discuss about faster reaction and then better yield and higher purity. Based on experimental data, it has been found that microwave enhanced chemical reaction rates can be faster than those of conventional heating methods by as much thousandfold. The microwave can use higher temperatures than conventional heating system, and consequently the reactions are completed in few minutes instead of hours. For instance, synthesis of fluorescein, which usually takes about 10 hours by conventional heating method, but can be conducted in only 35 minutes by means of microwave heating. better yield and higher purity. Less formation of side products are observed using microwave irradiation, and the product is recovered in higher yield. Consequently, also the purification step is faster and easier. For example, microwave synthesis of aspirin results in an increase in the yield of reaction from 85% to 97%. Energy saving. Heating by means of microwave radiation is a highly efficient process and results in significant energy saving. This is primarily because microwaves heat up just the sample and not the apparatus, and therefore energy consumption is less. Next, uniform and selective heating. In conventional heating, the walls of the well bulb get heated first and then the solvent. As a result of this distributed heating in an oil bath, there is always a temperature difference between the walls and the solvent. In the case of microwave heating, only the solvent and the solid particles are excited, which results in uniform heating of the solvent. Selective heating is based on the principle that different materials respond differently to microwaves. Some materials are transparent, whereas other absorb microwaves. Next, green synthesis. Reactions conducted using microwaves are cleaner and more eco-friendly than conventional heating methods. Microwaves heat to compounds directly. Therefore, usage of solvent in the chemical reaction can be reduced or eliminated. Synthesis without solvent, in which reagents are absorbed on mineral support, has a great potential as it offers an eco-friendly green protocol in synthesis. The use of microwaves has also reduced the amount of purification required for the end products of chemical reactions involving toxic reagents. Next, reproducibility. Reactions with microwave heating are more reproducible compared to conventional heating because of uniform heating and better control of process parameters. The temperature of chemical reactions can also be easily monitored, but there are some limitations of microwave assisted synthesis. These are yield in a smaller scale, the use of microwaves as a source of heating has limited applicability, improper use of microwave heating for the rate enhancement of chemical reactions involving radioisotopes may result in uncontrolled radioactive decay, uncontrolled reaction and cause explosions, and also the health hazards, which is very much important. Even conditions may also result the uncontrolled reaction and cause explosion. Health hazards related to microwaves are caused by the penetration of microwaves. While microwaves operating at a low frequency range are only able to penetrate the human skin, higher frequency range microwaves can reach body organs. Research has proven that on prolonged exposure, microwaves may result in complete degeneration of body tissues and cells. It also been established that constant exposure of DNA to high frequency microwaves during biochemical reactions may result in complete degeneration of DNA strand. Here, a list of interesting and relevant scientific publications on microwave synthesis of last decades has been given here. Metal color catalyzed reaction, synthesis in heterocyclic. Here are so many publications: catalyst ligands complexes, oxidations, various organic transformation, nanomaterials, polymer chemistry, biodiesel, and biomass related applications. Thank you very much for your patient sharing.